I'd like to walk you through a practice problem now. You're going to love this. So here it is. You are flying an F-117A fully equipped, which means your aircraft weighs 52,500 pounds. You want to maintain equilibrium in straight and level flight at an altitude of 30,000 feet, cruising at 400 knots to conserve fuel. The aircraft's wing area is 1,140 square feet. At what angle of attack should the F-117A be set to maintain equilibrium? So the reason that aerospace engineers need to know this and need to solve these kinds of problems is for design of the aircraft. If solving this, if it turns out that the aircraft angle has to be set at 16 degrees, that's just way too steep of a pitch. So then they would have to adjust some of these factors. Maybe things like aircraft wing area, or even possibly setting maximum speeds or maximum altitudes or maximum weight. So let's get started on this. Here's some information that you need to know to solve this problem. You need to know how knots are related in meters per second. What is air density at 30,000 feet? What is the relationship between coefficient of lift and angle of attack? Well, here is a graph for this aircraft that shows the relationship between coefficient of lift and angle of attack, and that's for the design of this particular aircraft. So what I would suggest you do right now is follow along with me in your engineering notebook and write these things down with me. What you're going to find is that if you try to do all this in your calculator, you're just going to be stuck. So the first thing we're going to do is write down the equation. Coefficient of lift equals 2L divided by A rho v squared. And instead of rho, I'm going to use d for density. It just seems to clear things up a little bit more so you don't confuse density and pressure, because that seems to happen often. So if that helps you out, make sure that you do that. But just know that rho, that little slanted P sign, is also used to indicate air density. So first, let's take a look at lift. We know that in this case, if we are maintaining equilibrium in straight and level flight, lift has to equal weight. My upward force has to equal my downward force. So since I know that, I should be able to figure out the weight, and then I'll know the lift. Well, mass is 52,500 pounds. If I convert that to kilograms, then I get 23,800 kilograms. And I'm going to show you really quick the simple way that I do that. If I have 52,500 pounds lb to kg, and it just gives you the answer right here, 23,800. Now the reason I said 800 is because it's 52,500. There's three significant figures here, so I'm just going to choose to use three significant figures here, 23,800. So this is a really easy way to do conversions, unit conversions, when you're trying to work them through. I'm not going to show you the rest of those, but I just wanted to show you how I can get those so quickly. So I got 23,800. I know that weight is mass times gravity. So 23,800 times 9.8 is 233,240. And if I was doing this on my work, I would actually put a little box around this. I did it in red here. You don't have a red pen or pencil usually. So put a box around this thing, and then you know that that's a value that you're going to use up here, because I solved for weight, and that actually equals lift. So one piece down. Now let's take a look at area. That's our next variable that we're going to try to figure out. I know that the area, wing area, is 1,140 square feet. So I have A equals 1,140 square feet, and then I do that Google conversion, and I have 106 square meters. So I'm going to put a box around that answer because it's done. I know that I have the next piece of information that I need. You're going to see that I'm lining up the variables on the left-hand side. I did that intentionally. This slide took me like 2 hours to make, so appreciate that. All right, velocity is 400 knots. Well, we have to convert that too. And I said 400 with a decimal here. That means it's three significant figures. So when I convert that, I get 206 meters per second. So V is done. Box that one. Three of them done. The only one left I have is density. Sweet, I must be almost done. I'm not, because density is a huge pain. It's pressure divided by this whole thing, which includes temperature. So that means I need to know pressure and temperature. Let's look at temperature first. Here's my temperature equation from the atmosphere assignment that you did recently. To get this, I need to know the height. Well, it tells me 30,000 feet. So my height is 30,000 feet. I got to convert that to 9,144 meters. Well, that's not a final number, so I just made that black. I'm not going to box that number, but that's important. Now I can put that into my temperature equation and solve for T. And I get minus 44.3 degrees Celsius. Then I can put that back up here, but I got to find pressure first. So let's do the pressure equation. This should all be in parentheses. This 5.256, all of this is to that power. I just couldn't get the parentheses to kind of go around all that. So when I substitute the temperature in here add 273 divided by 288 to that power times 101.29. I get 30.17 kilopascals. Now I know pressure and temperature. I can put them in my density equation, and boom shakalaka, I get 0.466 kilogram per meter cubed. Now I have density. I have everything I need. This takes a while. There's a lot of calculations. You can say I had to convert almost all these values from standard to metric. Huge pain, but that's just life sometimes in problem solving. If you can do this kind of problem, you can do pretty much anything in problem solving in physics, and it really all has to do with organization of your data. So don't fight it. All right. Now we substitute everything in, and I'm showing my work. Don't just plug all this in your calculator and flip a coin and wish. Plug this or type this all out, print this all out on your paper, then type it out. Do the denominator first or the numerator, and you should get 0.222. So what the heck does that mean? Well, that's CL. I look at my graph. CL is 0.22, so somewhere right around here. And what's my angle of attack? My angle of attack is 1 degree, about 1 degree. Well, that's what I'm looking for. What angle of attack should be set to maintain equilibrium? If I set my plane at approximately 1 degree, then I'm going to maintain straight and level flight with this mass, at this altitude, at this velocity, with this wing area. So that's an example of a problem that includes almost everything with every possible unit conversion that you're going to need. So hopefully, if you walk through this problem with me, that'll make doing this problem or type of problem on the homework a whole lot easier.